So that's what we'll do at 5:20, but before that we've got 4 5-minute or so talks. And the first one is from Dominik Strutz, who is it working?
No.
Oh, you have to just do this. On.
Okay, thanks.
From the University of Edinburgh. Go ahead.
Okay, so hi, I'm Dominik, and today I will give you a brief primer on experimental design for interrogation problems. This work is done at the University of Edinburgh together with Andrew Curtis, and I will try to explain it with a simple example for you all to understand what it means. So let's consider this relatively simplistic seismic source location example. And here in blue you can see a prior probability density function, and this just means that's the information we have where events are likely to occur. So in this dark blue area we think it's very likely that an event occurs, and in this less light blue area it's less likely, but we have some idea where it's going to happen. And with that at hand we can then define our model space, which in this case is just the vertical and the horizontal component of our seismic source. And we now want to solve the design problem. What is the best design to constrain the hypocenter, which means to constrain the both components of our seismic source. And to do that, we first of all need a likelihood function, which just encodes how the physics behaves in our problem and what data noise we have. And the physics in our problem is just first arrival travel times, and we can then use the travel time differences to constrain the source. And here you can see the ray path of first arrival times, and you can see due to the complex velocity model in the background that is quite a complex problem and definitely non-linear. And this information here would be enough to solve the experimental design problem, but typically to complete it we also have the posterior, which gives us how likely is a model in model space given some observed datum. And I will use that to visualize the effects different designs can have in the end. So let's just...
I'm just down on this side so they can
Okay,
see
yes.
the screen and you.
Yes. Okay, so let's just solve this experimental design problem. And the best position for receiver is here on the top left. So this receiver gives us the most information about seismicity when we observe some datum. And I just simulated an earthquake here in the middle, took the datum, and got this exemplary posterior probability distribution. And you can see that it constrains especially the horizontal component quite well, but here the problem is the constraint on the vertical component is nearly not there. So now I want to introduce what interrogation theory means. Interrogation theory means that we want to answer a specific scientific question, and in this case the question is going to be, what is the best design to constrain only the source steps? And in this case this will change the best receiver location dramatically. But to do that, we can't work in model space anymore, because that's 2 coordinates, and we're only interested in 1. So what we need to do, we introduce a target space. And in this case, this target space is very simple. It's just the vertical component. And this mapping that gets us from model space to target space just takes our model vector, or source location, and spits out the vertical component. And with that at hand, we can again solve our interrogation optimal design problem. And here the best receiver is in the middle. And here you can see again an exemplary posterior probability distribution. And you can see that the vertical part is a lot better constrained, apart from this small area here, but this is quite light, so it's very low probability. And you can see along this line here, the horizontal component is not well constrained at all, but the vertical component is a lot better constrained on average. So here you can see that the design changes quite drastically depending on what question we pose to the problem. But why is that different, and why is that difficult to do in practice? So to solve the optimal design problem, we need a backwards mapping from target space to model space. And especially if we are talking about non-Gaussian priors and non-discrete functions, that can be quite hard. And since we don't know that mapping quite well, and even if we know it quite well, it's not too easy to construct the likelihood of going from target space to data space, and also the inverse problem. And those are quite hard, and we can't use the classical experimental design algorithms. And before I end, I quickly want to go through briefly how we can calculate these designs in practice. So let's again consider our 2 questions, the best design for the epicenter and the best design for the source steps. And we use a quantity so-called expected information gain, which gives us, for each design, an idea where it's good to place, in this case, this one receiver. And you can see here that for the epicenter, it's good to place it at either of the sides. And for the source steps, it's good to place it in the middle. And in this case, it intuitively makes sense. But as soon as you start to introduce a 3D geometry, more than one station, different noise, you couldn't do that intuitively anymore. So to summarize, expected information gain estimation for interrogation problems is not trivial, and you can't use many of the standard algorithms. And that's what we're working on. And to conclude with, for further updates and contact information, you can go to the website. And also, since there have been a few people asking about optimal design for DAS, we're going to have a small discussion in the coffee break Tuesday morning, and just anyone who's interested can come, and we just have a look, what do the DAS people need, what can optimal design provide, and just see, are there quick solutions, what do we need? So anyone who's interested is welcome. And also in general, if you want optimal design, you can always come to me, because I'm always looking for problems to actually make it useful for actual problems and not toy problems, because I think you get out a lot more of it. Thanks a lot.